This should be video Chem27CBlake. Yeah, I made some further refinements to my flip charts there from last year. This was the first page of the flip chart, and I showed how I went back and got this old periodic table of electronegativities. And here is the one out of this chapter, more or less the same thing. That's now in here. And then you subtract any two atoms from on there. It tells you the polarity in a bond and whether that bond is going to be ionic because it basically took the electron, or it's going to be non-polar covalent because they share pretty much completely evenly, or something in between called non-polar covalent where they share but not equally. And then you represent those with a dipole. Okay, and I had done methane, and then ammonia, and then water, and then something from the boron group, something from the beryllium group. And now we're going to look at ones that don't follow the octet rule because they have more than 8 electrons. The majority of the time you're in here with something that follows the octet rule. But there are things that don't follow the octet rule. And this is NBBR5, I think. We're not going to do that one. This is maybe SF6. NBBR5. We are going to use PCl5 instead, phosphorus pentachloride. NB's not even in that family. Okay, so if we did phosphorus instead of NBBR5, we did phosphorus pentachloride. That'd be niobium pentabromide, I think. If we did phosphorus pentachloride and you drew the Lewis structure for it, we'd end up with 40 electrons and we would have more than an octet. You'd have 5 and then 1 outside of that. Well, how do you do that one? Well, that's what this is for. If you look up in my molecule kit, this is probably a phosphorus. And what it looks like is this. A molecular shape of trigonal or trigonal bipyramidal. So you have a little pyramidal on top and a little 3-sided pyramidal on the bottom. So 1, 2, 3 sides on the bottom, 1, 2, 3 sides on the top. Bipyramidal, triangular each side. So it's trigonal or trigonal bipyramidal. Looks like so, looks like a jack almost. This molecule, even though this bond's polar, and this bond's polar, and this bond's polar, and this bond's polar, and this bond's polar, ends up being nonpolar. That's because top and bottom, these two dipoles cancel, and in the triangular section, in the part that would be triangular planar, let's do it this way. These dipoles cancel, and then these opposite dipoles cancel. So the molecule, even though every one of the 5 bonds in it is polar, ends up being nonpolar. That shape for this section, trigonal bipyramidal. Okay, SF6, that was the bottom one on that page 263, I think it was. SF6, 48 electrons total, sulfur in the middle. This does not follow the octet rule at all. In fact, I doubt that I have this one in here to show it to you. Let's try taking a look. 1, 2, 3. Yeah, I'm pretty sure I don't have it. It's basically a pyramid on the top and a pyramid on the bottom. It's an octahedral. It's an 8-sided figure. Its molecular shape is octahedral, I think, in this book, is what they call that. Yeah, trigonal bipyramidal, or bipyramidal is from a different book. But it could be called that if you take another chemistry course in college, you have to do molecular geometries. It could be called either one of those, or maybe even something different. The point is on that one is every bond is pointing in a different direction. So it's maybe I do have it. Yes, let me try to build it here. I do have it. I've got a couple of these in here. This type of kit here, by the way, is called an old knobby, and I recommend this for organic chemistry, but if you had it, it'd be helpful for this too. Okay, so I've got two this way that cancel, two this way that cancel, and two this way that cancel. So no matter how you look at that one, SF6, all the dipoles cancel, and the molecule as a whole ends up nonpolar again. That shape, though, for this section is octahedral. It's an 8-sided figure. If I could connect these, I'd have 1, 2, 3, 4, 5, 6, 7, 8 surfaces. Okay, going on to the next one. Make sure this is working right. Looks good. I am not doing these necessarily in the order in the book, so let's back up to number 38. A nitrogen trifluoride molecule contains numerous lone pairs. Draw its Lewis structure. If I draw nitrogen trifluoride, I need 26 electrons. I end up with them this way, and I end up with a bond this way, this way, this way, and nothing there. It's the nitrogen again. In fact, it would look like this, except it'd have green, green, green instead of white, white, white. So this is the same thing as the ammonia molecule. What shape is that? Well, you got a lone pair up here, pushing those 3 bonds down, or the lone pair on the bottom. I guess I'm looking at this one this way. So it makes a trigonal pyramidal. In our case, dipoles are out, out, and out. They don't cancel because they're not in a plane. They have a downward component each. Ask about that one if you're not sure. Next one, number 41. This is ammonium ion. When we did this one, it ends up the same shape as the methane molecule, where I have each dipole is in this time because hydrogen's about 2.1, nitrogen is about 3.0 on electronegativities from the table. This shape, tetrahedral, 109.5 degrees for every angle. Even though every one of those 4 bonds is polar on this ammonium ion, the ion as a whole is nonpolar. It doesn't have one side that's negative and one side that's positive. The whole positive charge that's shared on this polyatomic ion is shared equally. We don't know which one of these hydrogen atoms is the source of that positive charge. Okay, figure 14. This is from page page 258. It's draw the nitrate ion. We want to work some of these shapes for ions as well. Nitrate ion, you got 23 electrons in your nitrogen and oxygen atoms plus an extra one for that charge, gives us 24. When you draw that in, you keep getting 26. You have to take a pair off the nitrogen, move a pair in, we got a double bond. We haven't seen one of those in a little while. Okay, and so that shape, everything's in a plane. Valence shell electron pair repulsion theory says this will move down here and this will move down here and it'll be in a plane. Basically, it would be something like this. Oh. I guess if red was oxygen. Well, gotta go it this way, I guess. I have to do it with carbon atoms. But it would look like this. Okay, if I had some black ones or different colored ones in here. So it'd be this shape, but it should be 4 black ones. A double bond, a single bond, and a single bond. Now, they're in a plane, but they're in a triangle. So it's trigonal planar. And this is pretty nonpolar. You got a dipole from nitrogen to oxygen, because oxygen number is about 3.5, nitrogen's about 3, that difference is about 0.5. I don't worry too much about those numbers specifically. See, oxygen is 3.44, nitrogen 3.04. They're actually different by about 0.4 according to this table. So dipole that way, dipole that way, dipole that one. That one kind of counts twice, but it's shorter. You know, so is it polar or not polar? You could argue either way with that, but I'm going to argue nonpolar. Another reason to argue nonpolar is this one is in resonance. So it is an ion, it is a polyatomic ion, so we use a bracket with a charge, but it is also in resonance. Let's see if I did this right. So we also have a big bracket to represent resonance among all these 3 shapes of ionic polyatomic ion. And what that basically means is it acts like it's got some double bond character here, and some double bond character here, and some double bond character there. So all of these bonds and all these charge distributions are equivalent. So it doesn't have a polarity because it does resonance. Shape is trigonal planar. Okay, what about perchlorate ion from number 42? Well, that shape is going to be tetrahedral again. Top, bottom, and each side. Tetrahedral again. Like so. Everything's equivalent. Let's look at number 40 again. CS2. Same thing as oxygen's right above sulfur. So carbon dioxide has this same shape. A double bond to an oxygen, a double bond to an oxygen. Here it's CS2, so it's carbon double bonded to a sulfur, carbon double bonded to a sulfur. They're in a line. Now, this molecule is nonpolar for 2 reasons. One, sulfur I think is 2.6, its carbon's 2.5. This isn't approaching 0.4. There is not a dipole to draw on either one of these. And even if there was, they would cancel because they're linear, like this. So this one is nonpolar. There's no bonds that go into it that make it polar. And it's linear. That's the molecular shape. Here's one, nitrite ion. Supposed to have 18 electrons. We end up removing a pair and moving a pair. And so it's alternatively either one of these in resonance. Because there's an electron pair right here, it's not drawn very good here. Let me try it again. That electron pair, because of valence shell electron pair repulsion theory, is going to push those away, and it's going to push those away, and there's nothing here to keep these from being pushed together some. So the angles are about 120, about 120, and about 120. That's bent. So's this one, for the same reason. Molecular shape is bent. Is this molecule polar? Yes, because this one isn't opposite this one. They're at angles. And so those vectors are going to resolve out to where you have an overall vector dipole with a positive side here to a negative side there, a positive side here to a negative side here. And so that has a dipole either way. Okay, that's probably enough for this video. And this is 47C. 27C. Good, it's 47. We'd be finishing the year up.